Hello Chemistry. This video is going to allow us to perform some of the calculations that will appear in WebAssign. So, just a quick rehash before we get to the calculations. In this picture here, we're looking at the relationship between gas pressure and the number of moles, or the number of gas particles, right? Moles is how many particles do you have? How much gas is in there? What we find is that, and you knew this relationship before you even came into chemistry actually, you just didn't call it this. You know that if you pump more air into a tire or into a ball, it will create more pressure inside of there, right? Now we are acknowledging that to be adding more moles of gas in, and that will cause greater pressure. The reason is because pressure is based on the frequency of the collisions with the walls of the container. So if we have more gas particles, we are going to have more frequent collisions, which means higher pressure, right? And we said that they were directly proportional because of that. And this is just showing that air does have mass, which makes sense because mass is related to moles, right? So the ball on the left is more inflated and it's got more mass, so it's tilting the balance. All right, so the relationship between amount of particles, aka moles of gas, and pressure is that they are directly proportional. That means that when one goes up, the other goes up, but not just that they go up together, but they're in proportion. Or if one goes down, the other goes down. So for example, if we look at the left image compared to the middle image, if you were to physically count the particles, there are double the particles in the middle image. The pressure also proportionally doubled. If we had put 5 times the amount of particles in the container compared to the first one, the pressure would be 500 kPa. So this is a directly proportional relationship. From here on out, you need to be able to think proportionally. You need to be able to think of what effect will changing this have on that kind of thing. But yeah, so they are directly proportional, pressure and the amount of particles. Pressure and volume are another story, right? This relationship is referred to as Boyle's law. When we look at our graph of what happened with pressure and volume, which is what you did in your data, as the pressure goes down, right, as our y-axis goes down, the volume on the x-axis actually increases, right? That's why we're going down to the right. That's increasing. Or alternatively, you could look at this as volume decreases, going from right to left, pressure is increasing. So they're doing the opposite. This is what an inversely proportional graph looks like. It happens to be pressure and volume, but any two variables that do the opposite of each other proportionally will look like this essentially. So that was our relationship. The relationship between pressure and volume is that they are inversely proportional. When one goes up, the other one goes down by the same proportion. We also notice, if you look at your data from what we did, the pressure times the volume is equal to some constant value, right? Every time you did a trial of P times V, the number was roughly the same. Now, it wasn't perfect, right? Because we had some trouble stabilizing the temperature. So that was a little bit of experimental error, meaning that there were some inherent flaws in our setup. Nothing anybody did wrong. So it didn't come out perfectly, which is very natural. That happens all the time. But we want to look at the greater trend, which is that in general, P times V is some constant value. That's going to come up in a second. We also want to look at that if pressure versus volume itself is an inversely proportional relationship. But if you look at pressure and compare it to the inverse of the volume, or 1 divided by the volume, that relationship is actually directly proportional, and it actually passes through the origin over here. In other words, if pressure is 0, then the inverse of pressure being 0 is possible. They can both be 0 together. So this is what a straight line like that would look like. So they're actually proportional, pressure versus inverse volume, whereas pressure versus regular volume are inversely proportional. A reminder as well that this only works at constant temperature and the constant amount of gas, right? The moles of gas are not changing if this is going to work, right? For you kept your apparatus sealed the whole time you were looking at this relationship in order to not let any new gas in or let any of our current gas out. We kept the amount of gas constant. This is the relationship. This you can actually do the math with, which we'll see in a second. Okay, But so if we look at this relationship, if we go from the left one to the middle one, notice how the amount of particles is staying constant. And we're also going to assume constant temperature. The only thing we're changing is pressure and volume. If we went from this container to that container, the pressure was divided by 2, going from 100 to 50. The volume ended up being multiplied by 2. So they do the opposite of each other, but in proportion. The pressure is divided by 2, the volume is multiplied by 2. Going from the middle to the last container, if the pressure is multiplied by 4, the volume was divided by 4. We went from 2 to 0.5. So they do the opposite, but in proportion, by the same factor, by the same number. And this is just showing, this is repeating that. This is called Boyle's law. So we can use this for our calculations. And here's a visual of that happening. Okay, so very important skill to have from here on out. By the time we finish this unit, there will be like 10 different kinds of calculations. And you need to be able to keep it straight and know what you're looking at. With a problem like this, you want to first acknowledge what you have. You need to acknowledge what you actually have in the problem to know which equation to use. It says we have a volume of 946 milliliters. I would find this in your slides, pause the video if you need to. Label that as V1. V subscript 1. That's your first volume. And it's at a pressure of 726 millimeters of mercury. That's your P1, P subscript 1. The reason is because this volume is occurring during this pressure. They are paired together. So we're calling this P1 and V1. What is the pressure of the gas in millimeters of mercury if the volume is reduced at constant temperature to 154 milliliters? That constant temperature just means we're allowed to use this rule. We're also assuming that the amount of gas is constant because they didn't say otherwise. So the only things we're changing are pressure and volume. Because we are only changing those, we can use this rule, this equation. The first pressure times the first volume is equal to some constant, right? Some constant value. We can use that to figure out the rest. They gave us the other volume, so we can use that to have only one variable left, P2, and solve for that. So we've got P1, V1, P2, we don't know, and V2. Okay. Before we even solve this problem, you should be thinking in the back of your mind, based on what you know about the relationship, what kind of answer are you expecting? The volume is going down from 946 to 154. Therefore, the pressure in our final answer should be higher than the original pressure because they do the opposite of each other. So in order to set this up, there's a couple different ways you could do it. The way that I recommend is manipulating the algebra first. Taking this generic equation and manipulating the variables before you even plug anything in. If you can do that, that will be the easiest way for you going forward to be able to find this and make sure everything's neat and tidy. Alternatively, if you're not as comfortable with that, you could literally just plug in the numbers for this one and solve accordingly. You could plug in P1, V1, V2, divide both sides by V2 to find your answer. This is just doing that before you even plug the numbers in. And we end up putting this in like this. This is also nice because it helps us see that our units canceled. Tracking your units is always helpful to know if you're doing things right. The fact that we're left with pressure units means that we're probably on the right track. Our final answer is higher than the original pressure, which is expected. And also it's 3 sig figs because each of our numbers in the problem only had 3 sig figs. Okay. Now we're going to take a look at what happens, the relationship between volume and temperature, with everything else held constant, right? We're looking at 2 variables at a time, and that's it. We can tell from the graph here that as temperature goes down, the volume also goes down. So that is actually a direct relationship. What it turns out is that it's actually directly proportional. So, in our image up here, we are keeping the number of particles constant. We're not adding more particles in, so n is constant, n is the number of particles. we are keeping our P constant as well, our pressure. So when you heat up a container like this or a balloon, the only way for the pressure to stay constant is if the volume of the container expands. Think if you had and the opposite of if you had a container that didn't expand. If you were to heat it up, you know the pressure would build, right? You can kind of sense that. A sealed metal container, heat it up, you know pressure inside would be building until it blows up. This doesn't blow up because what happens is the volume gets larger and relieves that pressure increase. So this law that we're about to look at relies on the pressure and the number of moles being constant, and we're changing T and V, temperature and volume. So the answer is that temperature and volume are directly proportional. As we heat up our gas particles, the particles move faster, and they then collide with the walls more frequently, which would cause increased pressure, except for the volume of the container increases to keep the pressure constant. This only works in a container that's actually flexible. In a rigid container, it wouldn't work. So this is that relationship. It's called Charles' law. The way that it works, if you look at it, think about the way proportions are in math. This over this equals that over that. That's how Charles' law works as well. It is a proportion. Volume over temperature. The first volume over the first temperature is equal to the second volume over the second temperature. So look, if we doubled the temperature here from 300 Kelvin to 600 Kelvin, then the volume would also double. Something else that's very important about this is that the temperature that you use has got to be in Kelvin, right? The only way this will work is if the temperature is actually in Kelvin. The reason is because if you remember back to learning Kelvin at all, when you reach 0 Kelvin, that's absolute zero. We've not actually been able to even get that cold. That's impossible. Well, so far it's impossible. At least it's theoretically impossible. But so if we were to use Celsius temperature, this would not work at all. The equation would not fit. It would not work. And the reason is because it's very easy to have, for example, 0 degrees Celsius. 0 degrees Celsius is the temperature that water freezes, right? So that happens all the time. If you put 0 in the denominator like that, you have an undefined problem. The other thing is that the Celsius scale is just pretty much based on water, right? 0 is when water freezes. 100 is when water boils. It's not actually directly related to the particles and their motion. The Kelvin scale is based on particle motion. It's actually based on the kinetic energy of the particles. And at 0 Kelvin, all motion stops. So all that to say, you have to convert to Kelvin or this problem will be 100% wrong. To do that, you take your temperature of Celsius and you add 273.15 to it. That's it. So always do that first. Get to Kelvin and then go from there. Don't even chance it. Just convert immediately. Get to Kelvin. So a sample of carbon monoxide occupies 3.2 liters at 125 degrees Celsius. At what temperature will the gas occupy a volume of 1.54 liters if the pressure remains constant? Okay. So in this problem, P is constant, right? And it doesn't say, so we're assuming the number of moles of gas is also constant. The only thing changing is volume and temperature, so we would use this equation accordingly. V1 is 3.2 liters. T1, we already converted to Kelvin, actually. It's got to be in Kelvin. V2 is 1.54 liters. We don't know what T2 is, right? So at this temperature, it's this volume. That's why they're both V1 and T1. We associate them together. At this volume, it's this temperature. We're trying to figure out what the temperature is, the second temperature. So these numbers just are labels. They're not actually involved in the math, if you haven't realized that part yet. One way to do this is to isolate T2 first, right? What I recommend, I don't know if you knew this for math, it's very difficult to solve for a denominator, right? It can be challenging. The best way to do it is to flip the equation, flip the script. Make this into T1 over V1 equals T2 over V2. As long as you flip both sides, that's mathematically allowed, believe it or not. Once we do that flip, it's easier to see that that we can actually just move things around that way. So that's what I recommend doing. And we can go over that more in class if you need to. But yeah, flip both sides. T1 over V1 equals T2 over V2. And then at that point, you would just divide both sides by V1 to get T2 by itself, which is what happened over here. So you need to write that out and actually try it out. You need to actually try this. This is going to be the downfall of some people. And again, we see that our units cancel, so we're on the right track. Also, we see that the volume went down from 3.2 to 1.54. So we would expect the temperature to go down, which it did because it was 398 and it went down to 192. Right? And our 3 sig figs was our lowest number in the problem. So then our final answer is 3 sig figs. Relationship between temperature and pressure, those are also directly proportional, but it has to be in Kelvin. If we double the temperature, we will double the pressure. In Kelvin only. Notice how in the Celsius did not double. That's very important. So we kept our number of particles constant. We kept our volume constant, right? The size of this container can't change. It's a rigid metal container. But if we doubled the heat in Kelvin, the pressure proportionally doubled. And think about why. The particles are moving faster proportionally, and they're colliding with the walls proportionally more often. We will look at this last law in more detail soon, but you can actually combine these. So this is where I'll leave you. This is called the combined gas law. It considers the relationship between pressure, volume, and N, which is number of moles, and the temperature, which must be in Kelvin. You can use this equation, and this is one of the only equations we'll give you on the test. You can use this equation to find the other equations. For example, let's say that you're only changing the pressure and the volume. So let's assume that N, the number of particles or number of moles, is constant and temperature is constant. If they're both constant, N and T, then that means they're the same on both sides. So we can cross them out. Oh, this is not crossing out as well as I would have hoped. But yeah, basically we can cross those out. And we're left with just Boyle's law, just the relationship between pressure and volume. That's what we're left with. But okay, let's say we have another problem, right? We can use this for every single problem. Let's say we had another problem where we were changing, the pressure was constant. So I'm going to go ahead and get rid of that. And the number of moles is pretty much always constant. The number of moles is constant. Now we have our relationship between volume and temperature pretty much exactly. So you can use this equation for any of the other equations. So this is one of the only ones I would really use essentially. Okay, we will go over more when I see you, but just be thinking about those relationships and take your time to write out the math. There's solved problems on the website if you need help doing the math. There is an upcoming Do Now quiz on what's called the ideal gas law, which is a little bit different in math. Actually, no, it's on this law. It's on the combined gas law. So you need to be able to do this law. You need to be able to do the algebra. So come and meet with me if you can't do the algebra. All right. Thanks for watching. Looking forward to seeing you guys later.